Right now, literally at this exact second, invisible signals are passing directly through your walls. They're bouncing around your furniture, traveling straight through your body, and beaming right into your screen to deliver information at millions of bits per second. Honestly, it feels a little bit like magic, right? We rely on it every single day, for work, for entertainment, for connecting with the world. But if someone stopped you on the street and asked, hey, what actually is Wi-Fi? What would you even say?
And you know, it gets even more mysterious when things go wrong. Have you ever been right in the middle of streaming a movie or downloading a huge file, and suddenly everything just grinds to a total halt? All because someone in the kitchen turned on the microwave to heat up some leftovers? I mean, why does that even happen? Well, in this explainer, we're going to completely demystify this tech. We are taking the invisible and making it visible.
Okay, let's just jump right into our roadmap for this. We'll be looking at 1. The invisible signals, 2. Frequencies, 2.4 versus 5 gigahertz, 3. Making the connection, 4. Traffic jams, and 5. Smarter networks.
All right, part 1, the invisible signals. So, let's step into the physical realm here. How does that blinking box in the corner actually send data completely wirelessly? Well, at its absolute core, Wi-Fi is just radio waves. It uses electromagnetic radiation to transmit data. And what's really incredible about this is that it's the exact same physical mechanism as the light you're using to see the room around you right now. The only difference? Wi-Fi operates at a much lower frequency than visible light, which just puts it outside the spectrum our human eyes can pick up. But make no mistake, it is physically flying across your room right now at the literal speed of light. You just can't see it or feel it. But how does a wave of pure energy actually hold a YouTube video or an email? It does this through a process called modulation. Basically, the router physically alters or modulates the wave to encode data into it. It can do this by varying the height of the wave, which is the amplitude, or altering the speed of the waves, which is frequency, or even shifting the starting point of the wave, called the phase. Now, modern routers are seriously clever. Take QAM256, for example, which is used in the Wi-Fi 5 standard. It intricately combines both amplitude and phase variations at the exact same time to pack a massive 8 bits of data into every single symbol it transmits. It's literally like whispering a highly compressed secret code at light speed.
Moving on to Section 2, frequencies, specifically 2.4 versus 5 gigahertz. Think of these two bands like completely different types of roads. First up, you have the 2.4 gigahertz band. It operates at a lower frequency, meaning it has a longer wavelength. Think of this one like a long, winding dirt road. Because the waves are long, they can easily push through physical walls and travel way further through your house. But because it's such a reliable, easy path, absolutely everyone uses it, making it highly congested. On the flip side is the 5 gigahertz band. This operates at a higher frequency with a much shorter wavelength. This is your multi-lane, high-speed highway. It gives you dramatically faster data rates, but there's a catch. It has a shorter range and really struggles to penetrate dense walls. But hey, because fewer devices rely on it, it's beautifully uncongested.
Okay, Section 3, making the connection. So we know the physics of the waves and the highways they travel on. But how does your smartphone actually start talking to the router? Well, it happens in a very specific sequence. First, your router broadcasts its name, its SSID, on a narrow slice of a frequency band, which we call its channel. When you select your network, step 1 is the handshake. This is an incredibly secure WPA3 or WPA2 authentication process where your device and the router exchange encrypted credentials just to verify identities and set up a secure session. Next is the identity. Your device needs a name tag to participate on the network, so the router uses a protocol called DHCP to hand your phone or laptop its very own IP address. Once it has that identity, step 3 kicks in, allowing it to successfully pass data back and forth to the wider internet.
But wait, there's a slight problem here. Your internet service provider only actually gives your router one single public IP address. So how on earth do your laptop, your smart TV, and your phone all use the internet at the exact same time without all the data getting hopelessly mixed up? ENTERNAT, or network address translation. Think of NAT exactly like the mailroom of a huge apartment building. The entire building shares one single street address for the outside world, right? But the mailroom sorts all the incoming packages and delivers them to the individual private apartment numbers. NAT translates between that one public internet-facing IP and the multiple private IP addresses on your home network completely seamlessly.
Which brings us to Section 4, traffic jams and interference.
Here is where we tackle the real-world stuff that absolutely tanks our internet speeds. Let's loop back to that question from the very beginning. Why does your Wi-Fi slow down in a busy flat complex, and why does the microwave completely kill it? Remember that 2.4 gigahertz dirt road we talked about earlier? It is crowded. Microwaves, Bluetooth headphones, and baby monitors literally operate on that exact same frequency. So when you turn on your microwave, it leaks a tiny bit of electromagnetic radiation that basically just shouts over your Wi-Fi signals. Add to that the fact that if you live in an apartment building, your neighbors' routers are constantly broadcasting their own networks on overlapping channels. So the big takeaway here is that your router isn't just sending data. It's constantly battling an invisible wall of electrical noise just to be heard.
And this whole congestion issue brilliantly illustrates the gap between theory and reality. Check out this massive number, 9.6 gigabits per second. That right there is the theoretical maximum speed of the Wi-Fi 6 standard. It sounds phenomenal, doesn't it?
But reality check time. In the real world, you are honestly only ever going to see about 30 to 60% of that maximum speed. Why? Well, because of physical distance, the interference we just talked about, and the actual physical limitations of your own devices. Ever wonder why your bulky laptop is usually a lot faster on Wi-Fi than your sleek smartphone? It's simply because the laptop has enough physical space inside it to house larger, way more capable antennas than your phone does.
Finally, let's wrap up with Section 5, Smarter Networks and the Future. So how is technology actually adapting to this noisy, crowded, invisible world? Well, modern routers are basically stepping up to become ultra-efficient traffic cops. One of the absolute biggest game changers introduced in the Wi-Fi 6 standard is something called OFDMA. Before this, routers had to serve devices by taking turns, delivering a package to your phone, then to your TV, then over to your laptop. OFDMA allows the router to serve multiple devices simultaneously on the exact same channel. It's literally like swapping out a single delivery van that makes one stop at a time for an entire fleet of drones that can deliver packages to every single house on the street at the exact same moment.
Another massive leap forward is MIMO, which stands for Multiple Input, Multiple Output. Modern routers use an array of multiple antennas to send and receive several parallel data streams all at once. If standard Wi-Fi is a one-lane road, MIMO dramatically increases your throughput by instantly paving 3 or 4 extra lanes onto that highway, allowing way more traffic to flow through without slowing anything down. Then we have beamforming. You know, older routers used to be pretty dumb. They would just blindly broadcast radio waves out in a giant circle in all directions, just kind of hoping your device would catch them. Smart routers use beamforming to literally shape and focus the radio signal, aiming it specifically, almost like a laser, directly toward the exact device requesting the data. This drastically improves both your range and your overall network efficiency. And for those of you with larger homes or office spaces dealing with physical barriers that the signal just can't punch through, we now have mesh networks. Instead of one single router shouting from the far corner of the house, you place multiple communicating nodes around the building. They constantly talk to each other to provide a completely seamless blanket of coverage, automatically handing off your device to the nearest, strongest nodes as you walk around. It completely eliminates dead zones. And all of this builds into the very near future with Wi-Fi 7. This upcoming standard is going to push the boundaries even further. It completely sidesteps that congested 2.4 gigahertz dirt road by utilizing a brand new, wide-open 6 gigahertz band. But even more exciting than that is its introduction of multi-link operation, or MLO. With MLO, your devices won't even have to choose between bands anymore. They can actively use multiple frequency bands simultaneously, combining them to deliver totally unprecedented speeds and rock-solid reliability. So the next time you connect your phone, or stream a video, or, heat up some leftovers in the microwave, you'll know exactly what is happening in the air around you. The physics, the modulation, the traffic jams, and the incredibly smart tech holding the whole shebang together. Now you know exactly what those invisible signals actually are. So my final question to you is this: who in your house always blames the router, and when are you going to share this explainer with them?